Hello chemistry class. Today we're going to start our new unit on equilibrium systems. Lots of information to get through today, but the coursework won't be too difficult. So here we go. I got to tell you about 3 types of equilibrium in chemistry. Before I do that, I want to tell you what equilibrium is. It's a state at which no observable change occurs over time. Okay, we're going to expand that a little bit with the theory of dynamic equilibrium. But let me tell you about these 3 types of equilibrium. Okay, the first is phase equilibrium. So that's when a chemical exists in more than one phase at the same time. A perfect example is ice water at 0 degrees Celsius. The amount of ice in that water is going to remain constant over time. Okay. The second one is solubility equilibrium. And this will be reached when you have excess solute in a saturated solution. So if you keep pouring salt into water, mix it up, if there's any salt left at the bottom, the amount of salt in that glass of salty water will remain constant over time. You won't see any changes. The third most interesting one, the one that we actually will only care about in this course, is chemical reaction equilibrium. Okay, that's why I gave it stars and a crescent moon there. So I'm going to spend a lot of time today discussing this. And this involves reactants and products of a reaction. Okay? Let me get to this theory of dynamic equilibrium. Okay, so I'm going to use this theory of dynamic equilibrium, a balance between 2 opposite processes occurring at the same rate. Forgot an N there. Okay, so we're going to wrap our head around that using our first 2 examples. So for phase equilibrium, particularly ice water, which is our example, the 2 opposite processes are freezing and melting. So I mentioned the amount of ice in a sample of ice water at 0 degrees. The amount of ice would stay the same, but in reality, the actual molecules that form the ice, say if we dyed all the ice cubes so they were a bit different color than the water, you would see that some of those ice cubes are melting. Okay, but whenever a little bit of ice melts, some other water will freeze. Okay, so it's not that the ice cubes remain static. The equilibrium is dynamic, which means changing. So in a glass of ice water at 0 degrees, you will not see any change over time, but in reality, some of the ice is melting, just the same amount of water is freezing at the same time. I hope that makes sense. Let's talk about solubility equilibrium now. So in the salt water, the 2 opposite processes would be dissolving and crystallization, or maybe you prefer the word precipitation. So some of the salt at the bottom of your really salty glass of water would be dissolving into the water, but at the same time, some of the salt in the water would crystallize, would become powder at the bottom. I think those are easy to wrap our heads around. For chemical reaction equilibrium, it's going to take a bit more work. So let's dive into that. What I want you to burn into your brain right now is that most reactions aren't complete, and it's taken until now in chemistry class for us to address this. So typically in a reaction, you consider reactants becoming products. And it's a nice reaction, like say burning gasoline, all the gas is gone, it's turned into, energy. Carbon dioxide, water, I want to talk about this reaction. If we combine hydrogen gas with iodine gas, we get some hydrogen iodide. This might already kind of spook you a little bit, these double arrows. We actually see those in our redox table. It just means we have to consider the reverse reaction as well, and we'll build to that. All right, so if we use stoichiometry, I want us to consider a mole of hydrogen with a mole of iodine. Okay, using the Stoich ratio, we would expect 2 moles of hydrogen iodide. I want you to agree with that. So in 1 mole of this, 1 mole of this, we should get 2 moles of this. In reality, we don't. We get about 1.5 moles of hydrogen iodide. Why is that? Well, it's because of this. In reality, not all the reactants become the products. Okay? Some hydrogen iodide molecules collide with each other and create H2 and I2. That's the reverse reaction of what we wrote down. So you can actually think 2HI turns into this. Because as this is happening, these 2 guys colliding to form these, Eventually you get enough of these that they'll start bumping into each other to form this. Okay? So these double arrows mean it goes both ways. These two turn into HI, but two HIs can turn back into this. And it happens. Okay. So what I've written down is 1 mole of H2 with 1 mole of I2 yields 1.5 moles of hydrogen iodide when we allow that system to reach equilibrium. Okay, which means just give it some time. The theory of dynamic equilibrium said equilibrium is reached when two opposing processes occur at the same rate. For a chemical reaction equilibrium, the two processes are the forward reaction and the reverse reaction. Okay, so remember we discussed phase equilibrium and solubility equilibrium as opposite processes. The chemical reaction opposite processes, forward and reverse reactions. Okay, so we've filled that in now. There it is, nicely summarized for you. At equilibrium, forward and reverse reactions occur at the same rate. So over time, the amount of all of these entities will remain constant. That doesn't mean that the same molecules remain in the same form. Some of the H2 is still going to react with I2 to form 2HI, but as that's happening, some of the HI is bumping into each other to form these guys. All right, this is going to be a longer video. I want to talk to you about percent yield, which is pretty simple. This is where the math will come in today, but really, really straightforward. Okay, to calculate percent yield, you do the equilibrium amount or concentration, okay, divided by the maximum amount or concentration, as long as they match. Don't do an amount divided by concentration, that doesn't make sense. Do number of moles divided by number of moles, or moles per liter divided by moles per liter. We will do both. The equilibrium amount is measured, but more likely, since we're all at our homes in quarantine, I'll give you the equilibrium amount. You determine the maximum amount from stoichiometry. Okay, so I'm going to do a quick example with what we've been dealing with, this reaction. The amounts that I described earlier, 1 mole of each reactant placed in a container, and the yield's 1.5 moles of HI. Okay, I'm going to squeeze in this calculation right here. So the equilibrium amount of HI, we're talking about products, was 1.5. We discussed the maximum amount using stoich. If it's 1 mole of this, 1 mole of this, multiply that by the ratio desired over given, it'd be 1 times 2 over 1. The maximum amount we could get would be 2 moles. Okay? When I do that calculation, I get 0.75. It's called percent yield. If you guys have been in my class, you know I think percents are overrated, but here we go. 75% is the yield of this reaction.